Hello and welcome to Learn Data. It's great to have you on this channel. I'm Nilesh, and in this video, we'll continue talking about Bayes probabilities and we'll look into Bayesian regression. Specifically, we'll talk about evidence approximation, what it is, and automatic relevance determination. So, both of these topics they are based on previously published papers. One is Relevance Vector Machines by Tristan Fletcher, and then there is another paper by Tipping. So I'll have those mentioned on the slides as I talk through them. Also, this particular video, mostly going to be a lot of math or equations. The objective is not to derive them, but just to show the starting point and end point of a particular equation set and why it is important, so that you get a conceptual idea about what's happening in the background. So this could be considered as an optional video as well. In next video, we'll do the actual implementation and look at some of the visuals of how this works. So let's get started. In previous video, we left off with this equation, which shows the Bayesian rule where W is the parameter and D is the observed data. So what we are trying to say here is that in this equation, we have this is the posterior, and this is the posterior probability which we want to find, and that is based on the likelihood. So this is the likelihood, and in addition to this, we have this is prior. So prior probability. So what is the prior information we have about the parameters W that can be used to update the existing parameters along with the data that we have? Okay. And this is for normalization. This is also called as marginal likelihood. Marginal likelihood. So based on this, then how can we use it for regression? So in case of in case of so this is general uh, equation about Bayesian rule. We have posterior is equal to likelihood into prior divided by marginal likelihood, and this is posterior, which is proportional to likelihood and prior. So we'll use both of these forms and in as we need them in upcoming slides. So before we get into that, I just want to point out a couple of things as shown in this particular plot. So here we can see that this on y-axis we have the values t, which are the target values, or this is the output, and on the x-axis we have the input values, which are the x's. Now, usually what we have seen so far in linear regression is that for a particular input x, we out when we are outputting a value for y, or in this case t, it's a single data point. However, with Bayesian regression, when we the output is not a single data point, it's a distribution. So for example, as shown in here, given the value of x0, we are trying to predict the output t, which is equal to this, which is based on x0 and the parameters w. So as you can see in this particular data, in this particular curve of data points, we are uh, predicting or outputting this entire distribution for one particular value of x0. And this distribution, then with this distribution, what we get in the output is the uncertainty associated with the is predicted value. So rather than saying just this is just one value, we also have we are predicting a range of values that are possible. And of course, the most likely value would be right here, which would be which would be at the highest point in this particular uh, uh, distribution curve, as you can see, and that is generally the mean of the uh, output distribution. And here, this equation tells that probability of t given the input x and parameter w, and these are the this is the variance. So we'll see later that we are denoting the variance by beta, and that is from that is a normal. So this is for the Gaussian normal. So Gaussian normal distribution uh, as shown here. So this again would be the variance part, and this would be the mean. So that's how the Bayes regression output works. And if you need to find more information about this, I recommend checking out this reference that's at the bottom of the slide. The book on pattern recognition and machine learning. It has a really good introduction on this, and the book is available free of cost, PDF download if you look in Google. Now moving on, let's look at some Bayesian regression. So here, if we so here what we have is this equation, which is um, probability of the parameter w, which is based on all these uh, factors that are shown here. We have the input data, we have the output, which is the target, and alpha and beta are the hyperparameters, and they are related as shown right here. Now this posterior is proportional to the likelihood multiplied by the prior, and the likelihood is given by this part, which is the probability of t given x, w, and beta, and then we have the prior given as probability of w given alpha. Now the objective here is to maximize the posterior value. So maximize the posterior distribution by finding the most probable value for w. And when we solve this problem, when we reach the final output, this is the equation we get. And after looking at this equation, we have seen this before, uh, as this part is the sum of squared error, as we can see, and this part is the regularization term. So that's how the uh, regularization, similar to the ridge regression, can be brought into the Bayesian regression as well. Now moving on, let's look at what these parameters likelihood and prior indicate. So here the prior is based on a normal distribution with a zero mean as shown here, which is zero mean, and we have the variance. Now for likelihood, it is the product. So this particular sign right here, that's the product, similar to what we have for summation. This is the product sign. So we are multiplying the values of Tn in the distribution for different values of n, small n. Again, we have the mean and the variance right here. Next, now we are switching gears to look at evidence approximation, and the paper that I'm referencing here is this paper by Tristan Fletcher, Relevance Vector Machines Explained. In this video, we'll go over just the outline. If you need detailed explanation, I'll suggest reading through the paper to get more insight. Here, what we have is the very first equation for linear regression. We have the predictions y, which is equal to the parameters w transpose x plus c. So c is the offset. Now we can write this equation in this form with basis functions. So the value of c is included in the basis function right here. Thus, if we have n training examples, then we can write this equation as shown here, where the probability for t is again depend on the number of inputs xi, parameter w, and the variance sigma squared, and that is based on the product of this term right here. And in the output, what we get is we have t minus phi into w, where phi is the design matrix, which is all the features, values for the features, and w are the parameters or the weights. Now based on that, we can move forward and see uh, what we have. So here we have this equation, which is similar to what we have seen before, where we have this posterior is equal to the likelihood into prior divided by the marginal likelihood. Now with this, if we in the paper, this particular part cannot be calculated, so this entire equation can then be reformulated in as shown here, where we have this probability of w, alpha, and sigma square given t is equal to these product of these two terms right here. So then the goal that we have is to find the values of w, alpha, and sigma square that maximize the posterior probability that's shown here. And to do that, we need to find solve these two terms that are on the right hand side. Is the first term, which is the probability of w given t, alpha, and sigma squared, that can be so that can be rewritten here as shown, where the sigma squared is replaced by beta, and that comes from a normal distribution with mean of m and variance of sigma. So here in previous slides we are denoting mean by mu. So here we are denoting it by m. That's just because that's the notation used in the paper. So the sigma is given by this equation right here, and the mean is given by this equation. And we'll come back to this towards the end of the video, where we'll see that if we differentiate these two and set it to 0, then that's how uh, uh, it can help remove irrelevant features such that the values for w would be set to 0. And then we have the second term, which is this one. This can be rewritten as shown here, and within this term then the probability of t given alpha and sigma is equivalent to the probability of t given alpha and beta, and that is the product of integral product of the probability of t given w and beta and probability of w given alpha. And we'll see how each of these two terms are then calculated. So as shown in this slide, this term is calculated to this particular form, and the second term t and w given alpha is calculated to this form shown right here. And one point to note is that this is based on the zero mean Gaussian. So we have a zero right here. That's the mean, and this is based on mean that is not zero. Now the final objective function that we get, uh, which is shown here on this slide, the marginal likelihood, which is the probability of t given alpha and beta. So this function is converted to a log function, which is log marginal likelihood, as shown here, which is log of p, log of probability of t given alpha and beta. So this is the function that we want to maximize uh, by using the hyperparameters alpha and beta. So this is the main equation that uh, is used. Now in that equation, to calculate the alpha and beta, here as we can see, the alpha is calculated by this part, which is gamma I divided by gamma I square, and then beta is calculated by this part that is shown here. And once the alpha and final, that's a iterative process, and once that is found, once we have the alpha and beta, we can then use that along with a new value for x to predict t, which would be the new prediction. And then this prediction will be a distribution. It won't be a single data point, so it's going to be a predictive distribution which is based on these parameters. And finally, if we look on this particular equation slide, many of the alpha tend to infinity, so most of the alpha would can go up to the value of infinity. And so when we are looking at the variance and mean, which are based on alpha, as the distribution of alpha tends to zero mean and zero variance, in those cases the weights for those alphas would also be zero. And because the weights are zero, their corresponding input values xi would also be zero, and therefore those features or x values that have weights of zero would be removed or pruned, uh, and those could be the less relevant features. And only the features that remain then are those that have non-zero weights, and those are called as the relevance vectors. And that's what the relevance uh, means, or relevance vector machine refers to in this particular uh, method. Now moving on, let's look at the algorithm. And again, this is from the paper Relevance Vector Machines. So if you need additional information, I highly recommend checking that out. So the first step is to select a kernel function and uh, create using a design matrix, using it to create a design matrix, and then setting a threshold value such that that can check on the values of alpha as the iteration proceeds. And also you can set a threshold value of for alpha, so as to know if that value is above or below that threshold value to stop the iteration. And we want to initialize the values for alpha and beta, and then calculate the mean and variance based on these equations, and use that mean and variance to update the values for alpha I and beta. And once that is done, we want to remove all the alphas and the basis functions where alpha the value of alpha is greater than the value for alpha threshold was set in step number 3. And after that we want to repeat the steps 5, 6 and 7 until the convergence criteria is met. So that's the algorithm for relevance vector machine. And in this particular case, once we have then the final values of alpha and beta calculated, those can then be used by this equation to calculate the new target value. And again, the new target value would be a distribution rather than a single data point. And we also have the variance associated here with the new input that is given by this equation. So I hope in these couple of slides you got some intuition about what's how the Bayes theorem is used in machine learning, especially in case of the Bayesian regression or the relevance vector machines. And for code snippet, it's the same standard format. We import linear model, we have the data, and then perform initialize variable reg using the linear model dot Bayesian ridge. This is the Bayesian ridge, so it has the regularization built in, and we want to fit it to train data and then predict on the test data. That was it for this video. I hope in this video then if it was not super helpful, if you're looking for a derivation, I'll recommend checking the publications that I have cited on the slides. But at least you got some intuition as to how Bayesian regression works, what is the importance of the parameter W, hyperparameters alpha, beta, and the variance, and how the Gaussian distribution is kind of very important when we are dealing with this type of regression method. In next video, we'll look at actual implementation in Python and also compare the output of Bayesian regression with the methods that we have already studied previously. So please like, share, and subscribe. If you have any comments about this type of video, which is full of math and equations without derivations, but just an outline, let me know if you found this helpful. Uh, I'll see you all in the next video. Thank you.